So it's Sjoert, Sjoert, Sjoert.
Okay, excellent.
There we go. Thank you. But I respond to anything that starts with sh, so just don't sh me.
After you say your name 3 times, something dramatic happens.
Yeah, right? It's kind of scary, yeah. Okay, let's start. So I'll be talking about Assassin 14 Li as well, and about radio observations. And these were done not with the VLA, but with a different radio telescope in the UK. You can see it's in the UK because it's cloudy. It's called the AMI array. And so I'm really happy to be speaking at the end of this great radio session. So I knew all of my introduction slides would be covered. So I'll be taking like a slightly broader introduction and talk about jet launching in general. And so here's a picture from the Blandford-Snayak original paper where they have a disk, they have magnetic field, and propose a mechanism to launch jets powered by the black hole spin. And these ingredients you, I think, always need. You need a disk, you need fields. But how, where, when do we launch these jets? A different way to answer this question is, why are only 10% of quasars radio loud? And this is an histogram of the radio versus optical luminosity. And by radio loud, we mean these sources that are sitting here at the far end that have a lot of radio luminosity compared to their optical. So somehow 10% or so of quasars are able to produce these jets while the rest doesn't. And there's one popular way to explain this, which you can summarize in the spin paradigm, which is that the jet energy is extracted from the black hole spin by tangling the field in the ergosphere, and then the radio loudness that we see reflects the spin distribution as the black holes grow in cosmic time. They spin up, they spin down, and you have a distribution of spins, and that explains the distribution of radio loudness. And this is a really beautiful theory. There's like this big source of energy there that you can tap. So you could call that a theory bias. Something is beautiful, but it also works. If you simulate black holes in magnetohydrodynamic simulations, you can power these Blandford-Snayak-like jets. And there's some evidence that that this also works in nature, although this is a debate among people observing X-ray binaries. So let's not go into that. But let's talk a little bit more about X-ray binaries, which you could also argue are a great laboratory for studying jet physics and accretion physics. So here is what people in that field always make, a hardness intensity diagram. The hardness is simply a color. It's the ratio of two X-ray bands. So this is the hard band over the soft band. So here the source is hard. It has a power law spectrum. If we stay here in this diagram, this is a single source. As the luminosity goes up here, the intensity, that means the accretion rate is going up. And at some point it makes a quick switch. The spectrum completely changed. It becomes a soft state, like thermal, like we see in thermal tidal disruption flares. And what is very important is that every time a source makes a loop through this hysteresis diagram, there is a steady jet here, and then as it makes this transition, there's a radio flare, and in the soft state, there is never a jet. So this is just what you observe. And that brings us to the M dot paradigm, you could say. This is not widely used, but let's call it the M dot paradigm, the accretion rate paradigm. So if you launch a jet from the disk, and you say that jet launching is coupled to changes in the accretion state, you could explain the radio loud supermassive black hole population with this same paradigm if you assume the accretion is scale invariant, which means that everything scales with the mass. So we now go from stellar mass black holes to supermassive black holes. You get a factor 1 million, 10 million for the mass. And so all the time scales are longer, and here are low luminosity AGN, like liners, or which have a low accretion rate, and steady jets. That's indeed observed. Now here you would have the radio loud sources that are making this transition. These are quasars, but we know, of course, there's one problem here. Radio loud and radio quiet quasars have the same optical spectrum, so their hardness in that sense doesn't change. So this analogy doesn't completely work. But additional evidence for the scale invariant view of accretion is that neutron stars produce jets, and even white dwarfs, which don't have a black hole spin, they're non-relativistic objects, also produce jets. And now we move to stellar tidal disruptions, which are our favorite laboratory for studying astrophysics. Now, the question basically you could ask is, where do they land on this hardness intensity diagram? Do they make this transition? And this is, of course, great that we can test this using supermassive black holes. And there is a change in the accretion rate, we think, unless circularization is completely inefficient, and you always have a very low accretion rate, but we do observe large flares at least. And in that case, you could anticipate the launch of a jet, and these two papers were produced or written before these jets were observed. And we have seen these jets, beautiful talks by our previous speakers. And these state changes are probably already observed, although they're maybe not what we expected. But if I look at this is a power law decay, which is interesting. It's t to the minus 5/3, so there's a linear coupling between the fallback rate, at least theoretically, and what comes out in this jet. So that is already an interesting piece of jet physics that is not often discussed. So it's a linear coupling, it seems, and then a really quick drop. And I think the only way to interpret this is that there is some kind of state change. I don't know what triggers it, but I think the change in accretion from super-Eddington to sub-Eddington is a natural time scale that sits here, but I don't know if that's the answer. But I do think it's a state change that we are seeing here. Now just a quick recap of Asaf's talk, the timeline of jetted TDEs that we've seen so far. 1999, Rose had started finding tidal disruptions, and Stephanie followed up a few of them in the radio, but we had no detections. But in general, it wasn't very much on our mind. Then we've seen these 3 jetted TDEs, and they were discovered by their jet emission, not by their disk emission. And then we got really excited. 2014 is now, and that was last year. We've been doing lots of follow-up, but no strong candidates until now. And let me just quickly, if you've forgotten over coffee, summarize the follow-up that we've done, right? I've done some follow-up. Jeff Bauer has done follow-up of all X-ray TDE. I did all optical TDE. There were 2 detections here, but I think it's now clear, like among us as a community, that these were not in fact tidal disruptions, but probably a Seifert and a background source. And recent papers of recently discovered TDEs also have radio upper limits. So we've been staring at the radio sky, but no detections. We can put these on a plot like this. This is the Swift 1644 jet simulation here at late times. All these different curves for different viewing angles start overlapping. Now I think Jonathan made a good point that it could be that if you have a lower density, the jet stays relativistic for longer. But it is clear that at least jets similar to 1644 are not detected. And I think, with the work of Alexei, I think for most density profiles, all these upper limits are clearly inconsistent with any sort of radio jets in the thermal tidal disruptions. So that's the conclusion. No radio emission from thermal tidal disruptions so far. Jets like 1544 are not produced there. And this clearly is a challenge for the scale invariant view of accretion. I mean, if you see a jet once, why don't you see it again? Right, so this is a challenge for people that like that model. And then along comes the SESSEN, of course, and 14Li, which is our poster child source of this conference. So let me show you now the data of a SESSEN 14Li in a slightly different way. I'm not sure if it was shown already like this, but I like this plot. Here's observed frequency, and here is nu F nu, this is the output energy or flux. And this is the host galaxy photometry in gray, all archival data. You can fit a galaxy synthetic model to that. And then here's the first epoch of Swift UVOT observations after the source was discovered. Huge flux increase. And here is the X-ray data, which is also a black body, but you see these two will clearly not match, so it's not a single black body. Also a huge flux increase with respect to the row set upper limit here. And what is important to point out, I think we've seen this in the talks, trying to understand these tidal disruption flares as when we include the scattering, the talk by Nathan Roth. Maybe we should start reporting power law indices, not only black body temperatures, and in fact this power law index is alpha of 1, so it's not on the Rayleigh gene still. So maybe that is indeed consistent with some of these more advanced advanced radiative transfer models. But extending the spectral energy distribution, there is also an archival radio detection here shown at about 1 gigahertz from the NVSS and first surveys back in the 90s, as shown by Kate also. And this is really interesting because this is clearly below any level you would expect from star formation. So this must be due to an AGN. So there was an AGN in this system. But it's not your typical quasar AGN. If we look in the optical spectrum, there's no signature of an AGN except for this narrow O3 line here. This is the H beta absorption line. Here's the O3 emission line, and you can imagine if this is a really low redshift source. As you put this source at higher redshift, you would not see this O3 line. And in the same way that archival radio detection is at 2 millijansky, the flux limit of all these radio surveys is about 1 millijansky. So if the source would be a factor 2 further away, we would not see it. So that's important to keep in mind. Maybe this is not special that this was an AGN because it's in the Green Valley. That would be really interesting. But in this case, we know it is an AGN. And you can call it a jet-dominated accretion flow or an ADEF, but it's definitely not a radially efficient source. It's on this hard state. And I think the source is very similar in the optical to previous TDEs. So here's the plot that I made in 2011 from Sloan data, but now updated with all the new tidal disruptions that have been discovered since. Here is SS and LI. So this is a color-color diagram. So here is the bluest part of this color-color diagram. These are all the AGN in Sloan. These are supernova, which are typically less blue. So if you're a TDE skeptic, I hope that this can also convince you that, we're really seeing a separate population, and SS and 14Li is no outlier in that sense. Also, of course, the X-ray temperature that we observe is similar to previous X-ray selected events. And I think also the light curve of this event is very similar to what has been seen before. Here is the near UV light curve, luminosity now, ergs per second, and time since discovery is what I'm plotting. This is the famous PS1 10JH, which is really the best sampled tidal disruption in the optical. And you can just move this light curve up and down and left and right, and you can get a good agreement. So you can get a really good agreement between PS1 10JH and SS and 14Li, except that this source shows more scatter than 10JH, which would be interesting if you are thinking about reprocessing models. And these other curves on top of here, these two are power laws, which also go through the data, but an exponential fit, which would be a straight line on this log linear diagram, clearly does not fit the data. And I'm not married to a particular power law, but if you fit the power law index and you leave the time of disruption as a free parameter, you can express the power law in your favorite theoretically expected one. And so if it is minus 5.1 plus or minus 0.4 over 3. So it's close to 5/3, even if you allow the time since disruption to vary. So that's interesting. And the time since disruption in that case is pretty close to the peak. I think it's only about 30 or 50 days. Okay, here's again the optical light curve. Here's the X-ray data in blue. And interestingly, at late times, it falls onto this same 5/3 power law. So if you would be observing this in the Rosette survey, you may get 1 point here and 1 point a year later. And so indeed, it would also look similar. It would be consistent with a 5/3 power law, except for this early plateau, which we haven't seen before, probably because of the sampling. Yeah?
X-ray light curve consistent with the Miller light curve?
I think I believe so, yeah. We could use they have higher signal to noise to fit the temperature. So we could use their temperature to extract the flux, right? This is integrated flux. But I think it's pretty bright in Swift, so it should be consistent. We can really fit the temperature in each epoch to extract the total flux.
You might want to expect that.
Yeah. They don't have multiple epochs, right? They don't.
Well, they put a number.
Or they also plot the Swift data. I don't think that.
It's Swift data that's plotted in the light curve. I think that the issue that pileup being a problem.
for the lowest channels.
Yeah.
Yeah, but I think this. I mean, here it's getting fainter. So if it's pile up, then what would you get? How would it diverge from this?
Well, crudely, they have paper out of as a what an eighth of a future ago, and it noticeably higher in early.
Okay, so maybe it's T to the. Maybe it's getting closer to the power line.
No, actually, it looks more like the
Okay, but here we're getting quite faint, so I don't think pile up should be an issue here. Yeah, that would be good to look at. Like, this is my first exploration into X-ray data, so so this is also new for me, or not also, but for me it's new. Okay, so this was all public data. Now let's move to the AMI observations. So here is on the same scale. It's our 16 gigahertz AMI observations, and we got 2 epochs also at 1.4 gigahertz. From the Westerbork radio telescope, director's discretionary time. And so before we go and talk about how to fit this data, it should be pointed out that this source, right, was an AGN before all this happened. So here is the level of emission you would expect if that previous AGN would have stayed active, if it is a flat spectrum AGN like all of these ADEFs are. So we are, in our first observations, which are consistent, of course, with Kate's because we're looking at the same source, we are already below that previous AGN. So without like talking about what this means for jet launching, it definitely means that the previous jet has been terminated or is being terminated. So I think that is really exciting. And also, when I first saw this, I thought that was what we are observing. But if you go through the numbers, I think the termination of that previous AGN jet goes really fast. As was pointed out by Tsi, there's inverse Compton effects which will cool the electrons. So you can get rid of this previous AGN very fast. And in fact, what we're seeing here is the effect of a new jet that was launched. And so our approach was to model this with a mildly relativistic jet that is being decelerated. And that's like a Nakar and Perron model. And then if you do this, you get a natural fit for an energy of 10 to the 48 ergs. And so we are seeing here the self-absorption frequency cross at about 150 days, which provides one constraint. But otherwise, we are not fitting every epoch, obviously, because we have only one frequency here. But this line still goes through the data. So I think that it's encouraging that we can reproduce this slope without fitting each epoch individually, but just taking a single model which predicts that we are seeing a relativistic jet that has now started to decelerate.
What frequency was the pre-outburst radio measured?
That was 1.4, so that would be this line.
So I guess the difference is you're assuming a flat spectrum, whereas Kate is assuming a new to the -1.
Yeah. And you can turn this flat spectrum into a new to the -1 if somehow you remove energy from this previous jet faster at high frequencies.
But it wasn't known to be flat.
No, I looked everywhere, but there's only this data. We don't know the high frequency pre-flare radio emission.
There's a distribution of power loss in the spectrum from AGN.
Yeah, but if you have these AGN jets, right, and they are, you're looking at, and you have a compact self-absorbed source, and it's small, so it's unresolved, right? Then it's always a flat spectrum just from the equipartition, like Blandford-Koenig jet model. So that's what we assumed here. That's how the source looked like before we started observing. If it is steep, then this line would go down a little bit. Yeah. Here and here? Yeah, that's a good question. I didn't look into that, so I don't know. We can do that. Yeah, I mean, you wouldn't really expect it because they're at such different scales, right? I mean, with the delay maybe, but I don't think we have the fidelity to tease out like a delay plus a correlation. So And there's of course one more thing to point out here. These are previous upper limits, the best ones available from PS 111AF and PS 110JH. And both of these are inconsistent with or would not observe a source like this. And at late times, we have many more of radio observations somewhere here, and they are all somewhere here, I should say, and they are all clearly inconsistent because this source is fading so fast. Okay, so we have seen the first thermal tidal disruption with variable radio emission, and the first important conclusion is that we can say that the AGN, that jet that existed before this flare, has been terminated, and this can happen quite fast just because these electrons are no longer accelerated, they're streaming out of this jet, and at the same time they're also being cooled. And we model this radio emission with a new jet that is launched with an energy of 10 to the 48 that was mildly relativistic, and we are now observing the deceleration phase. Now, if you take this energy, which you need to fit the amplitude of the radio emission, then you infer this density, which is just the density you need for this jet to decelerate. So this is independent of equipartition assumptions. It's just taking this energy, saying you need to decelerate this jet. Now this density, which is 1000 per cc, that is actually consistent with what you get if you just if you have Bondi accretion that is feeding the pre-flare AGN. Right? There was an AGN in this source. It needs to get matter from somewhere. If that's due to spherical Bondi accretion, at the radius where this jet decelerates, we get of order this density. So these two are a good consistency check. And so this means that this pre-flare accretion flow has collapsed. It's gone now. And this flare would be a radially inefficient accretion disk which produces hard X-rays. We now have really good hard X-ray upper limits in the SWIFT data. And indeed, we are not seeing any hard X-rays from this source. So this is also consistent with the collapse of this pre-flare accretion flow. And so this is a natural analogy with X-ray binaries as they move from the hard to the soft state. And so if we extend this analogy, it would be reasonable to say that every thermal tidal disruption launches a jet, at least if it's first in the hard state, if it has a pre-existing AGN. Now further implications beyond the radio. So there is a dichotomy. We have to now really explain where this huge difference in jet power comes from. We also have the first X-ray and optical bright tidal disruption flare. And we also have X-ray upper limits from existing optical flares. So can we hide these X-rays from an inner disk by obscuration? And would this obscuration also produce the optical photons? That would be like one really beautiful unification model. Alternatively, you have this plateau at early times in X-rays, or maybe not really a plateau. But if this is roughly constant, that also looks like inefficient circularization. So that could also be a conclusion there. And so we now have a new timeline where in 2015 we have the first jet from a thermal TDF, and we could hope to expect more. And so thanks for the attention.
So I have to apologize in advance. I'm actually coming down to which means that my question may be even less coherent than usual. So you pointed out, of course, that in order to create these strong jets, we need both magnetic field and some relatively high spin for the massive black hole. And suppose we take at face value some of the rate predictions that Nick and others mentioned, maybe a few times 10 to the 4 objects falling in, a few times 10 to the minus 4 objects falling in per year. That means that in a Hubble time, you are accreting something like 10 to the 6, a few times 10 to the 6 solar mass. So if you actually have a massive black hole with a mass of about 10 to the 6 solar masses, then assuming that you just have random inclinations for the accreting objects, for the tightly disrupted objects, you tend to revert the spin towards 0. Or, for example, if you assume that there isn't sufficient accretion, but you have the eccentric accretion model that Lee and Gilad talked about, then basically, you just have material falling in without bringing in any angular momentum, but because the mass is increasing, you still have a dimensional spin that's dropping.
Mm-hmm.
And so now you find that for low massive black holes, you potentially end up with relatively low spins, whereas for very massive central black holes, like 2 times 10 to the 7 solar masses, if you accrete 10 to the 6 solar masses onto it, even with some random angular momentum, nothing much happens with the spins. So could this suppress
the jet formation for the lower massive black holes.
Yeah, so I think if you believe if you adopt the model that spin is powering these jets, then it's interesting that you could spin down these events with this kind of accretion. I mean, you could also have chaotic accretion, which would do the same thing, right? And I think still the amount of mass you can gather from just ordinary accretion is probably a more significant source to consider if you're making these kind of estimates. But that could explain why it seems that only the highest mass black holes produce relativistic jets, right? Which you would not necessarily expect. So you could add this in as another parameter, and it would probably go in the right direction. So I think it's a good thing to explore.
So I'm trying to understand chronologically what's happening with the radio. So in early times, there was radio emission, just at one frequency, you don't know the slope. And now it seems if you assume the flat power law, that the radio emission now is less than what that flat slope would have implied 15 years ago. Right? You had a green line,
Yeah.
and now it's gone down below that line.
Uh-huh.
Does that mean that the tidal disruption outflow has cleared out whatever gas is responsible for generating the radio pre-flare? Like, where is that radio emission actually going?
Where does it come from? So I think the way I think about this, right, is you have this pre-existing 8F-like flow, which is continuously powering a jet, which is at 10 to the 16, 10 to the 17 centimeters with its self-absorption frequency, right? That's your standard conical jet. The first thing that happens chronologically is a tidal disruption happens, you destroy this pre-flare accretion flow because it's fairly low mass. So that's what we assume. Now, if you just like in 1644, right, you turn off the central engine, then there will be a delayed response in the radio. And so what would have happened if we would have observed, say, at maybe 200 days earlier, is we would have seen this line go down rapidly, which is the pre-flare jet, which is just running out of electrons to produce synchrotron emission.
So when's the time of disruption relative to the first observation in this model?
Well, we don't adapt a time of disruption per se, because we can't really constrain it without doing modeling. But if you take a t to the minus 5/3 power law to be your disruption, then this shut off could happen a few days after that, and then the jet launching time can also be a few days after that. We can't really tell because it's close to being a self-similar solution now, so we've forgotten when this jet was launched, right? Because it's being decelerated. So that is not a parameter in our model.
Follow-up question on this. So since you have an AGN, eventually blows up a radio lobe that is larger than the jet that comes out in the TV, then you would have electrons sitting out there that will not clear that, and they still have to cool down and produce radio emission.
Yeah, that would happen on a much longer time scale. So,
Yes, exactly.
yeah.
So in that case, you should still have some contribution in that pre-existing AGN.
Yeah, I think that's a possibility. I mean, we could do some estimates. I think the energy output by this 8F-like jet, they don't blow lobes into their host galaxy, right? It's not an FR1 source. It's really wimpy. So I'm not sure how much that would give you. But in order to constrain that, you would either have to do low frequency observations or do VLBI to see how much flux is compact. I think there is some evidence for for variability, right, as scintillation. So that would mean that the flux is compact that is there. So it's not something big.
Yes, I had a couple of questions I'd love to discuss with you in detail offline, more details of your modeling. But I'm curious what you assumed for the opening angle of the jet.
Yeah, so we have it at 0.1 radian. Yeah.
So that we, as I mentioned, we had a very hard time making our full spectrum of observations fit with any kind of relativistic model
Yeah.
like that. So I'd be curious to see whether this model could also explain the full spectrum of the observations.
Yeah.
I don't know if you've done any of that.
Right. Yeah. So your paper appeared on the archive. So we looked at the data, and we can, even though we didn't know about it beforehand, but I mean the trend that we are seeing at higher frequencies is roughly consistent. I mean clearly there we don't expect that this model would exactly reproduce it. But I think to answer your first question, like here the jet is decelerated already, whereas you are simulating an interacting jet, right? So this is a really different model. So we don't have this opening angle constraint in that sense.
You're saying it's accelerated to quasi-spherical.
Yeah. So in that sense, our models are not that different.
Yeah, and the other question was, so you're relying on the self-absorption peak from the 1.4 gigahertz observation?
Yeah.
So how much do those two flux points actually provide? It looks like...
Yeah, it's significant, but it's 20% or so, yeah.
So we did a scintillation calculation based on we had two epochs of observations that I didn't actually show this plot. We had two that we took within 2 weeks of each other.
Yeah.
And we actually saw about a 20% variation in the LNet flux over that period. So we were assuming that was scintillation in terms of the average of those two.
Yeah.
Thing. And we did a calculation for what amount of scintillation we expect based on the size of the curve. That seems a reasonable amount. So I'm curious how if that difference you have there is due to scintillation or not, that actually.
Yeah. I think we can't rule that out at this point, obviously, right? So I mean, if it's scintillation, it's really constraining what the pre-flare emission is. Then it must be small, and in that case, I think it's hard to get it to be steep, which is how you model it. So I think that is. But that is. I think we just have to either wait or get more data to constrain this pre-flare emission, radio emission.
A very basic one. How do you estimate the Lorentz factor of the jet, and how much are we sure that this radiation actually comes from it?
Yeah. So if it's really subrelativistic, then you run into brightness temperature problems. And so, but our Lorentz factor is an assumption. So we say, okay, we're going to model this with a relativistic jet that has decelerated. If it's Lorentz factor 5, you probably run into problems with the energetics, with trying to fit the amplitude and the radius where it decelerates. And so if it gets to a really low Lorentz factor, you get a model similar to Kate's, but then you have the problem of the density being very low to allow this low velocity outflow to not be decelerated. You can also turn it around. I think that's really cute. I mean, if you say that this is due to Bondi accretion, then you get immediately to this 10 to the 3 per cubic centimeter. Then if you assume an energy, or if you assume a deceleration radius, you get an energy, and then it has to be relativistic too in order to be modeled in the Nakar and Piran. But we can say if it's 2 or 3, obviously. Yeah.
Okay, I think we'll continue this discussion in the discussion session. So thank you, Jan.
Thanks.
Okay, we're switching back to optical. For the last two talks.